difference of two squares. So this is a method of factoring in which we can factor a binomial as long as it is a difference and each of the terms are perfect squares. So a lot of times you'll see difference of two squares referred to as dots. So D, O, T, S. And it's really important to notice that there are certain circumstances which are required in order to be able to factor a difference of two squares. First of all, it needs to be a difference. There needs to be a subtraction sign between the two terms. Second, both of the terms need to be perfect squares. Now, this works as long as the exponent for a variable is even and the number over here is a perfect square. So it can be any combination thereof, but if it's a variable, the exponent must be even, and if it is just a whole number, it needs to be a perfect square. So when that is the case, you are allowed to write this as a product of two binomials where the first binomial is the square root of the first number. So if this is x squared, the square root of that is just x. And then the square root of the second number, so the square root of 36, is 6. And then one of the terms is positive, or one of the expressions, I should say, is positive, and one is negative. So if you multiply that out, it will give you x squared minus 36. Because the signs are different, middle terms are reduced, and that's why we're left with the binomial. So let's take a look at a couple of examples. If I was to make this a little bit more complicated, such as 4x squared minus 25. This is still a difference of two perfect squares because they're separated by subtraction. Both the 4 and the 25 are perfect squares, and this x squared is a perfect square. So in this case, you'd set it up much the same, and you would take the square root of first the 4x squared, which is 2x, because the square root of 4 is 2, and the square root of x squared is x. One would get a plus, one would get a minus, and then I'd follow it up with a 5. Okay, so again, as long as everything's a perfect square. One example that I want to show you that you cannot do. So let's say I have 100, which is a beautiful perfect square. I have x squared, and let's say I do plus 4. People get really caught up on this because I have some beautiful perfect squares here. I see an x squared, but I cannot do anything here because of this plus. Okay, because of this plus sign, I cannot use a difference of two perfect squares. I can plot a GCF, but I cannot use dots. Okay, so this one cannot be factored using dots, only a GCF. Now, when you get into more complicated circumstances, I'll give you one more example. You might see something like, I don't know, 49x to the 4th minus 81x squared. So there's just a lot going on here, but this is a difference of two perfect squares. There's subtraction, and then all of the numbers are perfect squares. 7 times 7 will give me 49. 9 times 9 will give me 81. And all of my variables have even exponents. Okay, so I want to take note that I can write this as a product of two binomials. I can put the square root of 49x to the 4th as 7x squared in each of these. I can make one of them a plus, one of them a minus, and then follow it up with a 9x. So this example in particular, you probably should have factored with the GCF first, but if they asked you to factor it using a difference of two perfect squares, this would be your final result. It's also very important to note that if you're ever not sure if something is a perfect square, you can find out in your calculator. The button next to the 9 on the TI Nspire has all the magical buttons in it, and you're going to look for a square root. So let's say you weren't sure if 49 was a perfect square. You can put the 49 in that square root symbol in your calculator, and you'll get a result of 7. Because it's not a decimal, you know it's a perfect square, and you're ready to continue. This was factoring a difference of two perfect squares.